you for giving me this opportunity to speak here as well as visiting here. It's been already great. So let me just maybe briefly review some of the things that's generally happening, and then I'll go right into the main point. So the idea is that in the last few days, let me also tell you the references. This work is by Alok, in collaboration with Alok, and it's in this paper. But the main background, a lot of background for this stuff is in these two papers where they analyze the asymptotic symmetry aspect parts of this talk. And the crucial input from the amplitude side was given by in this paper by Elvang and Elvang, Jones, and Coolidge, where they worked out high derivative corrections to the subleading soft photon theorem as well as the subleading soft graviton theorem in general effective field theories. So the general developments essentially I think summarize in this essentially the picture that's called the infrared triangle. So what's essentially been understood now is that seemingly there's this sort of ubiquitous triangle of equivalences in the infrared sector of any theory which has massless particles. One vertex of this triangle is the study of asymptotic symmetries. In flat spacetime near Scri plus. Another vertex of this triangle is the study of soft theorems. And the third one is what's called memory. And the nice thing about this triangle is that there's a sort of algorithmic way to go from one vertex to any vertex of interest. So if I know one side, I can use the algorithms that have so far been derived to work out all the other vertices as well. So for instance, the classic example of this triangle is one in which on this side you have super translations, which was something that was derived by Bondi, Metzner, Vanderberg, and Sachs in 1963. And the analogous soft theorem to this symmetry was basically Weinberg's soft graviton theorem. Which was in 1965. And the memory aspect of this is it's the so-called Christodoulou memory, or nonlinear or linear memory, which was by Zeldovich and Polnarov in 1974. So this equivalence is sort of very interesting because a priori these are three different topics studied by three different types of physicists. Zeldovich and Polnarov are experimental relativists. They were interested in studying properties of gravitational waves that have the potential to be measured. In 1974, they did not have LIGO, so they were trying to work out other properties apart from just the oscillations that could potentially be measured. They came up with memory. Of course, memory is an order G Newton smaller than the wave, than the amplitude of the oscillation, so it's not strictly speaking easier to measure in any sense. But the nice thing about it is that it's a DC effect. Once the wave has passed through, the memory stays forever. So you can take a long time to measure it if you want, and you'll always be able to pick it up.
All these three aspects also apply to any massless?
That is currently the belief, and given the number of examples that are popping out, we believe that to be ubiquitous. And the point of my talk is to show there's another case in which this is also true, where you might naively think that it couldn't possibly be true, but it also works out in that case. So yeah, we believe it's ubiquitously there in any theory of massless particles. Super translations, on the other hand, were studied by BMS. So they're formal relativists. They were more interested in the study of the structure of GR in flat space-time. And Weinberg, of course, was a particle physicist, and he was interested in the structure of scattering amplitude. So they're very totally different topics, and they've been each, as you can see, developed for like 50 years or so. But this triangle is very nice because it tells us that this is a classic example in which all three sides were known for a long time. But it's very nice because I can take one side. If I know one side, then I can deduce all the other sides. So one useful, for instance, if you say an output, another thing where you can apply this feature came about in the study of super rotations. which is something that BMNS could have seen in their original work, but unfortunately they did not have the work of BPZ to guide them. They only studied the global SL2C, but there's actually a whole Virasoro extension which is called the superrotations. This was first pointed out by Banks in a very tiny footnote, which I think lots of people missed. And so this was known since 2003, but the remaining parts of this triangle were not known, and it was then, once we knew about the existence of such a triangle, you can take this side and generate all the others. So for instance, we use superrotations to deduce the existence of a subleading soft graviton theorem. This was conjectured by Strominger and then verified by Cacciazzo in 2014. And then the analogous memory, there's a so-called spin memory worked out by Pastersky and Sasha Zheboydov, 2015. So it's been quite useful to sort of deduce all these other interesting structures that, and of course after the discovery of such type of this extra soft theorem that people did not expect, the amplitudes community came in with all of their strength and deduced a whole bunch of extra newer and newer soft theorems. And there's an algorithmic way actually to, if someone tells me a soft theorem, I can just work out what the symmetry is corresponding to that in all cases. So that can always be done. So in particular, I'm going to talk today about the subleading soft photon theorem. So when Cacciazzo worked out the subleading soft graviton theorem, it was a brute force sort of calculation. He worked out a whole bunch of amplitudes in pure gravity. And he showed that the following structure existed. So I have an n+1 point amplitude with a graviton with momentum q and polarization epsilon. And I'm interested in the soft limit, which is when q goes to 0. And then the structure that he found was S0. Let me write it down. So S0 is the leading Weinberg's soft graviton theorem. This was deduced, of course, we know Weinberg told us about this in 1965. It's something that's order 1 over q. It's a Weinberg pole. S1 was the subleading soft theorem that was conjectured by Strominger and then verified. So this is order q to the 0. But what he also found in addition was that there's also a factorization occurring at subleading order. Now at that stage of our understanding, there was no symmetry attached to this extra piece. So there's an order q term, and it turns out there's a factorization that occurs in gravity to this order. Beyond this, there's no sense in which you can of course always write down, take any amplitude, you can always expand it. Beyond this, there's no sense in which you can understand the S3 term, for instance, as an action of some operator acting on some lower order amplitude. That interpretation goes away. So this is the limit to which the the gravitational amplitudes factorize in the soft limit. The analogous structure also exists for photons. So let me write. And here, in the case of photons, it stops at order S1. There's no S2. There's no factorization that goes beyond this.
I think this came up in an earlier talk.
Yeah.
From the covariantization point of view, what is special about second order? What is different between third order and second order? And from the point of view that Ashok can elaborate.
You cannot reduce the complete number. The Ritchie scale or Ritchie scalar Riemann tensor couple, covariantization will not carry over that.
No, that's just the statement. That's just a statement of non-universality of S2. The fact that S2 depends on the theory that you're considering. Shiraz is asking. So S3, there were some assumptions that okay. So in the proof that Ashok had, he wrote down the effective action, but then he had to argue that some particular vertices with some arbitrary number of guys, and I have some k momentum sitting here. The 1pi vertex has a certain fall off. I don't remember what the power over here was, in order to derive the soft theorem. And he showed that this fall off is only of a certain order. And so given that order, you can only go up to this piece. Yeah, that's the idea in their proof. Yeah. Okay, so in the photon case, it stops at S1. And now we would like to assign a sort of symmetry interpretation to, we know the symmetry interpretation to S0. I should have told you that the symmetry interpretation here is just a set of large gauge transformations. That is to say, a set of gauge transformations generated by some parameter epsilon that does not vanish at infinity. When we say gauge transformations, we usually think of functions that die off at infinity so that they don't affect boundary physics. But you can also consider general other transformations, which generated by functions which are non-zero on the boundary. They give you non-vanishing charges. I'll explain this in some detail later. And the Ward identity for those symmetries gives you S0. So the question was how to reproduce S1. So this was first tackled by this paper here, where, as I said, there's an algorithmic procedure. If I give you a soft theorem, you can just always go and write a symmetry. So they did that. They started from this S1, they wrote down a charge, but there was no physical interpretation. They wrote down some charge, and they used that charge to write down the action on all the fields, but there was no sense in which, it was not clear what that symmetry is, why that should actually be a symmetry in any theory of, in any gauge theory. So that interpretation was totally missing. I think the interesting structure came out when Alok and Miguel wrote their, I think, very beautiful paper in which they argued that another interpretation of S1 is the set of divergent gauge transformations. So these will be gauge transformations that in principle take you out of the phase space, and they diverge as you go to the boundary in a very precise way, which I'll describe. But they show that if I consider such gauge transformations, then the Ward identity for that gives you S1. Okay. Now Elvang after that wrote a paper to further show that unfortunately S1 and in the gravitational case S2 are not universal. If I add higher derivative terms, in particular if I add from a Lagrangian perspective, if I add dimension 5 terms in a Lagrangian, they'll contribute to this order in the soft theorem. Now this was sort of problematic from this asymptotic symmetry side, because a gauge transformation on the other hand has a sort of universal action on all of your fields. And so in principle at least it looks like the charges should remain the same, and therefore the Ward identity should remain the same. So how do we explain the fact that S1 is not universal from an asymptotic symmetry's point of view? That's going to be the point of that's going to be what I'm going to explain in the talk today. That it can be done, and at least this side of the triangle that I'm going to talk about today continues to hold. That this universality class still exists. The Ward identity changes in some way, and the soft theorem changes in exactly the same way. Okay. This was just sort of a brief review of everything that's been going on. Okay, so now that with that out of the way, let me write down some formulas. Is a divergent superrotation. Same thing. So I'm only doing this because it's fewer indices, but everything I'm going to say trivially extends, albeit it's very tedious, but you can also do it for gravity. Yeah, yeah.
So if you change the Lagrangian,
Yeah.
when you said that you were expressing the charges remain the same, why do they remain the same? You need to, depending on the Lagrangian, you get your contrast charge from order. So why should it remain the same?
Yeah, when you go up to infinity, when you go up to square plus, the point of dimension 5 operators is that they fall off like 1 over r. So they shouldn't survive when I go to square plus.
Unless you do something like some gauge transformation which will compensate it for this.
Unless you do a gauge transformation that's compensating for that. Exactly.
The set of large gauge transformations remain the same despite for the all non-universal.
Yeah, yeah. I'm still going to do a divergent large gauge transformation, but because the gauge transformation is now divergent, it sort of compensates for the fact that dimension 5 operators falls off at square plus, and the two mix in a nice way to give us something that's interesting. And it's the same argument can then be used to show that, you know, why do dimension 6 operators not contribute? Because they still, even despite the fact that I'm considering divergent gauge transformations, the fall off of dimension 6 operators is still very high, so that they don't contribute to this to the S1.
Is it that you are allowing your divergent gauge transformation that sort of allows you to get this dimension 5 operator?
Yes, yes. I choose my epsilon to be of a particular form. I mean, it's not arbitrary. I'm going to explain that it's not at all arbitrary, that there's really just one choice, and that choice gives you the word identity that you want.
So you're allowing divergent gauge transformations, but not.
Yes, I'll explain why it's okay to do that. Not arbitrarily divergent. I'll explain why that's okay, and why I'm allowed to choose one type of divergence and not another type. Yeah, that I'll explain.
In the same sense, why diffeomorphisms radius 3 are divergent in a particular method.
Yes. Yeah. Okay. So let me first tell you what the photon S0 and S1 are. Okay. So in complete generality, this is what Elvang has told us, that an n+1 point amplitude takes the following form. Where S0 is so this is the standard Weinberg-Soft theorem, soft factor. This I'm sure you're all familiar with. S1, E is the coupling constant, Q is the charge of the kth particle, Pk is the momentum of the kth particle. So as you can see, this is completely universal. It doesn't depend on the set of interactions. It only depends on what particles are present in this n+1 point amplitude and their momentum. That's all that goes in there. And as you can see, this is order 1 over Q because of that. This guy is order 1, and this is the angular momentum of the kth particle. So again, here the only input that goes in is the angular momentum and the charge of the kth particle. So this term sort of comes from the minimally coupled theory. So if I'm just doing pure scalar QED or just QED with no other extra terms, that's what is coming from the minimally coupled version of the theory. But then Elvang told us something more, which is that in complete generality, you can also have this extra term, which always has the following form. And let me write out what this form is. So in order to write out this form, it's best to go to some spinor helicity notation. And mk plus, and by plus I mean over here, if the photon I'm taking soft on this side has positive helicity, then the corresponding m that you get is so it's just that. And then f hat is just a particle changing operator. So it has no dependence on z, it has no dependence on q or k or anything. It just takes the kth particle and replaces it with a different type of particle. Now what exactly that different type of particle is depends on the theory. But you can already say a few things. So what's firstly interesting is that the entire kinematical dependence is given in this mk and is completely universal. It's independent of what high derivative term you're adding. That's the first interesting fact. Secondly, another interesting fact, this you can just do some very simple little group scaling, because if I have this mk factor scales like 1 over t squared when I do a little group scaling. So this fk factor has to be a particle changing operator that lowers the helicity by 1, so that the soft theorem is little group invariant. So it sort of fixes the structure. In other words, if the kth particle is a scalar, the only thing fk can do to it is to change it to a photon with helicity -1. So really the only freedom in this S tilde is just the interaction strength, the coefficient in front of the higher derivative term. So it's still pretty fixed. It sort of very loosely depends on the set of higher derivative terms. The structure is highly constrained. They derived it using a lot of amazing, I think, tools from the amplitudes. There's some complex deformations of the spinor helicity variables, and I think their paper is very, very interesting. Okay, so the goal of my talk will be to derive this and sort of explain the universality over here, and explain this fact that Fk is, well, the moment you know this structure, Fk, the fact that Fk lowers helicity by 1 is automatically fixed by little group scaling. So my goal would be to sort of derive this entire thing and prove why this is universal, independent of any other thing that you can get. Okay, so in everything I'll do, as again I'm saying it's sort of general, but for clarity I'll write every formula I'll write on the board will be for one theory, the simplest theory. But you can of course write it down for anything you want. So the theory that I have in mind for any formula that I write down is simply this. Has a Lagrangian that's very simple. So phi is just some neutral scalar, and it couples to, so this is some dimension 5 coupling and couples to the field strength in this way. And it's nice because it's neutral, because phi doesn't have any charge, so this S0 and S1, both of them are just 0. So the only non-trivial term in the entire soft theorem is just this. That's the only thing I care about. And in this particular theory, you can show that a state created by phi, when acted upon with this F hat, gives you a photon state with the same momentum. So if this state phi has momentum p, it has the same momentum. As I said, helicity -1 times this factor. And equals f p plus and we know this has to be 0 because there's no particle with state with helicity -2. But let me write down for completeness the set of all higher derivative terms. This was also worked out in Wang's paper. Basically the set of all dimension 5 terms that you could possibly have. Phi f squared, phi f f tilde, psi bar, and I can replace this with f tilde also. I can have or I can have h mu nu, t mu nu. It's the electromagnetic stress tensor, and that's the graviton. Well, yeah, I'm deriving it in perturbation theory at tree level. Yeah, so I'm assuming that they're. Yeah, so yes, you just think of this as some effective Lagrangian, maybe a 1 pi effective action, and I'm just doing tree level calculations in a 1 pi effective action. And so then these are the only terms that could possibly contribute. You only have to worry about the dimension 5 terms in that.
I couldn't get the notation because fixing the notation x.
So F is the field that creates the state. So in this case, it's a photon, the field strength. I'm not writing A because it's not gauge invariant. P is the momentum of that state, and plus or minus is the helicity of that state. So this is a statement that a scalar state, which doesn't have any helicity, I should probably have written 0. A scalar state, when acted on this with this operator F hat, gives you a photon of with minus. So this part we already knew using little group. It's only just a matter of fixing the overall coefficient, which of course depends on the strength of that interaction.
Is it the scalar state plus the photon or replaces the scalar state?
It replaces the scalar state. That's what this is doing. It takes the kth particle and replaces it with this new particle. So this structure is not new. This happens also, for instance, in the soft Fortino theorem, where you can just see by fermion number it has to have a it has to change fermions to bosons, and vice versa if you want a non-trivial amplitude. The fact, I'm writing everything over here, taking a positive soft limit. So f hat, yeah, I should have made it clear, plus minus plus minus. So I'm thinking of f hat plus minus. All of this is plus. So f hat plus is the factor that you would get if I take a positive helicity soft photon to be soft. Yeah.
Going back to your original system, triangle, universality, generality, how much of that is holds for continuous holds for non-abelian theories?
Oh, so non-abelian theories, yeah, it still continues to hold. Actually, it's the entire triangle holds for the leading soft theorem. Yeah.
And here you make a point that this non-universal substances in the subleading term
Yeah.
come from this high dimension operator.
Yeah.
But perhaps because you cannot try any other recasts. But in non-abelian case,
Yeah.
even without to go to this high dimensional operator, you could still make a recasted theory.
No, yes. And so again, if I have just minimal coupling, just plain pure Yang-Mills, then I just get this term. But this is just the complete general structure. This was derived using
So
some.
only higher dimensional terms contribute to this non-universal.
Yes, that's right. That's right.
And in particular, the coupling dependence doesn't show.
I mean, the
Any good for Yang-Mills, you say is asking does everything is independent lambda.
well, the coupling. I mean, it'll sort of show up here.
No, but there is
If
no,
the-
let's say, any good for not.
Yeah, if I just have an overall, yeah, then it won't show up. Yeah, it won't show up. You're absolutely right. Yeah, in Yang-Mills, this is just some number divided by E squared.
Well, there is no limit to 5 then.
Yeah, yes, in pure Yang-Mills, that's right. Yeah. Yeah, then it won't show up. It'll just be that. I mean, it just makes sense because this term just sort of comes from the 3-point amplitude only. That's the 3-point vertex expanded to second order. That's where this term is coming from. It's essentially, so where does this term coming from? Comes from essentially the fact that if I give you a P plus Q momentum state with a J mu, the U1 current or the conserved current on this side, and then I have P over here. So if I take Q to 0, this is completely universal because this is forward scattering of a conserved current. So Weinberg chapter 10 will tell you the exact form of this thing, and that's how this is coming. And if I expand this to subleading order, then that is fixed. So the leading order term is sort of fixed. You have to use gauge invariance, and now you have to use translation invariance. And here, if I have to use gauge invariance and I use rotational invariance, and I can fix even the subleading form. That's basically where this is coming from. So I just need some conserved current. That's all I need. Okay. Okay. So now I'm going to.
F hat plus and F hat minus for you?
That's a good question. F hat. Yeah, I've never thought about that. Let me see. So.
I mean, it does some kind of algebraic
I mean, they don't commute, though the product should preserve helicity, right? Maybe they do commute. So if I act on this state, this is just 0. Yeah, maybe the commutator is just 1, the identity. Because if I act on this with f minus, f plus up to some numbers, this is just the same as f minus. Because f minus raises this to phi p, and then f plus acts on it again to put it back down to this state. F hat minus acts on a negative helicity photon and gives you a scalar with helicity 0. So f hat minus raises helicity by 1. F hat plus lowers helicity by 1. That's the action, up to some overall constants. Should be? Yeah, that's probably right. Yeah, I think that's right. I think that's right. Okay. Okay, so I'm now basically always going to work on this axion gauge theory so that there is no S0, there is no S, except for one case, I'm going to always work there. There's no S0, there's no S1. So there's only this one term in the soft expansion, which is the thing that I'm currently interested in.
So axiom you have phi as
You can all, okay. Let me just, this is the action I'm working with. That's not right. Dilator. Okay. Okay, so before I go to the subleading case, let me quickly review the leading case, because essentially the arguments will be the same, and then I'll also use one result from the leading case. So just for this moment, because I now want to reproduce S0, I'm going to assume that the particles have charge. So the S matrix, of course, is I'm working in flat space-time. I have a set of massless particles coming in from sky minus. They interact in some non-trivial way, and then they go out on square plus. And the S matrix is to understand the structure of this wave function out here, given the wave function on sky minus. So in particular, to understand these soft limits where I have one outgoing soft photon, I need to study the structure of the theory on sky plus. So on sky plus, the coordinates that I would set up is these radial coordinates where I have r, which takes you towards sky plus. U is the null coordinate on sky plus, it's the null time. And then at every point on this sphere, remember we have a hemisphere. And so the z bar coordinates are just the stereographic coordinates on that S2. So the metric is just that's just the metric on the unit sphere. Okay, and for the gauge field, I'm going to work in Lorentz gauge. And in this case, it's not hard to convince yourself that the fall-offs for each of these fields are of the following form. Order 1 over r, and the idea then is to do a Taylor expansion with these leading coefficients, and then take that entire Taylor expansion, plug it into Maxwell's equations. Maxwell's equations itself has a large R expansion, and then solve order by order in R. Right? That's what I'm going to do. And so I'm just going to tell you the result of that enterprise. So this is the equation I'm solving. Well, in general, Maxwell's equation can always be written in the equations for any gauge theory can always be written in this form. And this J gets contributions from higher derivative terms also. I can always rewrite it in this form. So you can just imagine that such an equation basically will continue to hold even in higher derivative, in the presence of higher derivative terms. So the leading equation that I get for the nu equal to 0, nu equal to u component basically takes the following form. Actually, let me write that here because I'll use it later. standard fall-off conditions for electromagnetism. So the equation I get if I do a Taylor expansion, plug it all in into Maxwell's equations, solve Maxwell's equations order by order, is the following thing. And for simplicity, I'll call XA ZC bar. So this is just so let me explain my notation. This superscript with a number is, so Ju2 is the 1 over r squared coefficient in the Taylor expansion of Ju at r equal to infinity, right? So that's what J, similarly with all of these. So as I said, AZ has order 1, so its leading order coefficient is Z0. So that's what that notation means. Capital D is just the covariant derivative with respect to the sphere, unit sphere.
If I converted your boundary conditions to Cartesian coordinates.
Yeah. In Cartesian coordinates, it's just 1 over r. Everything falls up. So A mu, where mu is a Cartesian index, just falls up like 1 over r.
And that AR is 1 over r square also comes from that?
Yeah.
Why would be that?
Let me see. So AR is just del r x mu. Yeah, I can explain where that comes from. Right. So to leading order, this is just make a del r t, keeping u fixed. So this is just AU plus A0 plus A vector. Yeah. So now the point is let me just rewrite this in this form. This is basically 1 comma x hat mu A mu. This is this. But you'll see at large r, when I take that large r limit, the momentum that's sitting in here is precisely of this form, because this is precisely a null momentum. So this dotted function to leading order vanishes.
You're using equation.
Yeah. For all solutions, this is the structure. Yeah. Okay.
Is it follow-up condition situation of Photon or already got it?
I mean, I'm looking for physical solutions. So I'm taking all the solutions that has these sort of fall-offs. No. P dot epsilon is 0 is true no matter what gauge you choose. So that's where this was coming from. Okay, and here the argument is that I can integrate this and solve for FUR in terms of AA0. And this you can show works to all orders, and at the end everything is determined entirely in terms of these AA0, which basically is the statement that a polarization has, photon has 2 polarizations, because the entire solution, physical solution, is determined in terms of 2 functions of 3 variables. And those 2 functions, and these coordinates are nice because AZ creates a positive helicity photon and AZ bar creates a negative helicity photon. That's another reason stereographic coordinates are nice. You can work in a helicity basis. Okay, so the data is these AZ zeros. Okay, now what I would like to do, I want to construct the charge. So remember, right now I'm doing a quick review of the leading case. I want to construct the charge on Scribe plus. Now one of the issues for which I just need to covariantly quantize, and then I can just construct the charge using the standard Noether's procedure. One of the main issues is that Scribe plus is a null hypersurface, so you have to be a little bit more careful than the usual things that you're used to, because that's on a space-like surface. So what we do is we use this idea of covariant quantization, which
AU also part of the data?
AU is determined here. So okay, so I'm assuming that there are no massless particles, so there are some dynamical constraints I have to impose on the solutions. In other words, so AU, this is basically something to do with AU right here. I have to assume that this vanishes in the far future. That is just a statement that everything, just there's a finite region in which all radiation comes in, and then everything is pure vacuum in the far
And then
future.
the 1 over r square piece of AR is also there.
Is driven by other equations. There are. This was just the U component. There are other equations you can write down.
Okay. So let me understand the claim.
Yeah.
Is the claim that E is Z0
Yes.
completely specifies phase space of this theory?
Yes, AZ and AZ bar.
AZ and AZ bar. Now, I've asked you this before and we had some discussion, but let me just ask it again for clarity. Typically, I would think of the phase space of electromagnetism as being made up of 4 functions. And
Yeah.
there's 2 polarizations and
Yeah.
then function in first derivative.
Yes.
You're giving me a phase space made up of 2 functions.
Yeah.
Now, I know it's dangerous to count functions, but is there any intuition for this? This is this light cone business, right? I mean,
Yeah, it's the light cone. The point is that on the light cone, the normal derivative is the same as the tangent derivative. So specifying the function is equivalent to specifying its normal derivative.
right. So is there some sort of intuition about, these 2 functions have both positive and negative?
Let me repeat this. Yes, I remember the discussion. Yeah, so strictly speaking, when I do null quant, let's look at any point in the bulk. So I have some space-time, some general space-time. So if I want to quantize on a space-like slice, then I just need to prescribe my data on this space-like slice, and that's completely well understood. I need to prescribe phi and phi dot over here. Now, if I now instead, like I'm sitting on Scri plus, on Minkowski space, if I have a null slice that's sitting over here, actually speaking, I need to prescribe the field phi here as well as the field phi there. And those are the 2 datas that you're thinking of. But then causality fixes one of them in terms of the other. Because I want, for instance, the solution.
Sorry, are we 2 dimensions or?
No, let me just draw Minkowski space. Yeah. So one thing I can do is just prescribe it on such a slice. But if I want to prescribe it instead.
Wait, if with higher dimensions, shouldn't you just draw every point that is a sphere?
Yeah, every point is a sphere.
So you don't need to draw the left hand side.
Yes, let me just do that. Yeah. So just something like that. Or I can do something that looks like this, right? So let me look at look at Scri minus, then things are causal. I give you something in the past and something in the future is determined. So the idea is basically that if I was this sort of hypersurface, that's the full Cauchy slice. And I need to prescribe the data on this guy as well as the data on this guy. Those are the 2 functions. But now when I push it out to Scri plus, and then I also need to assume that there's nothing funny happening right in this region, that in the far, far past, everything reverts to vacuum. Then that just basically fixes this phi completely.
Is that the same as saying that there are no outgoing photons at very early depths?
Yes, exactly. So yeah, we put in these dynamical constraints that far past is pure vacuum, far future is pure vacuum.
Okay, so but you can take these 2 functions and rewrite them as 4 functions of space.
Yeah, if I was anywhere else in the bulk, then I would have to prescribe all of these 4.
Right, but now suppose I take the standard space-like.
Oh yes, then 4 functions.
4 functions.
Yes.
You think there's some way of getting those 4 functions in terms of these 2?
Yes, exactly.
Okay.
Oh, sorry. You were talking about photons. So here I'm talking about scalars. So there's phi and phi dot. So there's 2 functions here, and 2 functions and 2 functions here.
Right, but suppose now I take your prescription, but I'm going to ignore that.
Oh yeah, if I ignore that, yeah, then
there's only 1 function.
There's only
that
one.
should translate to 2 arbitrary functions.
Yeah, but that's fine, because even when I write down solutions here, I'm assuming certain nice structures in the if I do Fourier transforms
I
and
was just
whatnot.
worried about the 1 goes to 2. I know it's not very precise.
Yeah, I
At any
mean,
point you can do that.
it's a null slice, so it usually contains more information because it's sort of
Something like
causally
plus
connected.
minus, right? There's a radial momentum is only positive, but this guy goes positive and negative.
Yeah.
That would help me.
Yes, I think, yeah.
Something like that.
Yeah.
Okay.
Yeah, you're right. Actually, that's probably exactly the right. If I go to momentum space, in order to construct a positive energy solution, I need to take some linear combination of phi and phi dot.
Yeah.
And then a different linear combination gives you the set of negative energy solutions. But the same phi contains both positive as well as negative.
Yeah.
Yes, that's right. That's the right way to look at it. Okay. So quickly, let me go through this idea of covariant quantization, which allows you to quantize on any surface null or not, any Cauchy surface, so let S of, so this is sort of more general, let S be any action and phi be the set of all fields in my theory, every single field. And then as we know, we vary the action to find the equations of motion, and it always takes the form E phi so when I vary it, it's always of this form. I read off the Euler-Lagrange equations from this side, and then I have some boundary terms left over. And then these boundary terms, you can then use this to read off this theta, which is essentially like the canonical one form, if you're familiar with this geometric quantization sort of thing. As you can see, this you can't read it off uniquely. There's still an extra piece, which is a divergence of a 2 form that I can add here, and that does affect some of the physics, but it doesn't affect anything that we're interested in right now, so I'm just going to ignore it. Then you define, once you have that, you define omega mu, which is defined as the following, is theta. So this is a function of delta, and let me write it clearly. Exactly, exactly. Maybe that'll help. So it's P dq. As you can see, it's a one, not this exactly. If I integrate this thing on a Cauchy slice, then as you can see, this is a one form on phase space. It's taking in a variation, a vector, and returning a number. So it's a one form on phase space. That's sort of, you should think of that. It's not this one. This is called the symplectic potential current density. If I take d of this, that gives you the pre-symplectic form. So if I take the d of that, which is defined 1, 2, right? So this, as you can see, is basically just doing, it's basically an exterior derivative on phase space of theta. Yeah. Of phi? It's phi itself. Phi comma phi is a certain is theta function, is the sine function. Yeah. Unlike on space-like slices, when yeah, yeah. And then in order to get what's called the pre-symplectic form, you just integrate this. So you just integrate this on any Cauchy slice, and this gives you the pre-symplectic form. So this construction sort of guarantees that this omega is closed, but it doesn't guarantee that it's non-degenerate. So really, strictly speaking, what you then have to do is to factor out all the degenerate subspaces to obtain what's then called the symplectic form. We won't have to worry about those issues here.
Those are associated with gauge freedom.
Those are associated with gauge freedom, exactly. Yeah, so one does have to worry about it for a bit, but I'm not going to talk about those things. Okay, so this is the structure, and finally at the end, of course, we want to construct a charge. So the charge Q on a slice sigma that generates a transformation delta, any transformation delta. Whether this charge is a symmetry or not depends on the structure of delta, but you can always write down a function that generates anything on phase space. So the charge Q that satisfies the following equation. It satisfies the equation that delta of Q is omega sigma delta phi delta phi. So now that I've plugged in an explicit function over here, this thing is a one form, and now this is d of some 0 form, so this is a one form. And so this is the equation that I would need to solve on phase space in order to derive what the charge is. If it turns out that this is exact, then I can integrate it out and I can obtain the charge exactly. So in that case, it's called, this charge is said to be integrable if I can integrate it on phase space. So this is the way you construct any charge. So now let me just go ahead and do this. So I've told you how to do it in complete generality, so I'm not going to tell you the details of how to do this. For gauge theory, but this is just the answer. It's
Why do you call this delta?
this is the this is originally a 2 form. This is a 1 form. This is another d of some 0 form. So you should think of this as dq on phase space as some 1 form over here. Now if this 1 form is exact, then I can solve it. But typically it's not.
So the small delta is an arbitrary variation.
Small, yeah. So this side depends on delta phi. This side also depends. Yeah. So for each arbitrary variation, capital delta is the symmetry that you, or not necessarily symmetry, but the transformation that you would like to generate using this quantity q.
The particular parameters of that transformation will be
Will be it's all inside capital delta. So here we'll want to write down the charge when delta is a gauge transformation. So this is what it looks like. Plus complex number. Okay. As you can see, one of the things about this omega is that it doesn't depend on higher derivative terms. It's basically just given by the kinetic term, just f. And the idea is that any higher derivative term you write will just fall off too fast, and so it doesn't contribute at all. This is precisely the problem. Now I'm going to end up using this formula to derive the charge. If omega doesn't depend on high derivative terms, how could the charge depend on high derivative terms?
Suppose we repeat it just for a space like operation.
Yes, you can do all of that.
So we get a delta mu wedge delta.
Yeah, you'll get delta phi wedge delta phi dot.
Or here it will be delta A dot delta E. So that is maybe different.
Yes, exactly.
I'm confused with it. I was not
Uh, I made a mistake. Maybe let me just finish that. Yes, maybe I don't have this.
Well, so these deltas I thought were like vector fields on space. It was like, I mean,
Yeah.
small variation.
Yeah.
So normally in order to write wedge products, we have to go to the one form. So is there some kind of reasoning why?
No,
why can you put are these like usually
This is non-deterministic form. You can use the non-deterministic.
so that has been done, like that A.
No.
It's simpler than, it's just like the dxi is a vector field, but it's a basis for one form.
Yeah.
In ordinary differential geometry.
So these are like these.
Yeah.
But the other deltas that appear as argument of the symplectic form, those deltas must be vector fields, right? So those deltas there are vector fields.
Yeah.
And these deltas here are, some.
These
But
deltas
that-
are dxi with the property that dxi evaluated on the vector field delta xi
Yeah.
Right.
is del. Is del.
Yes.
These are the duals of.
Yeah.
Yes.
Sorry,
No. Okay. Okay, so this is basically the problem, but let me at least keep going and derive for you the leading soft theorem quickly. So if I do all of this for gauge transformation, so now I plug it in. The nice thing about gauge transformation is that you'll find that it's integrable. Yes.
You said you know the theta means writing capital theta.
Yes.
Capital theta.
They will affect boundary brackets, and they are important to understand. This is basically the issue that, for instance, that Ashtekar had not solved in the 70s that was confusing him quite a lot. They give you the brackets for the zero modes, and they are certainly important, but I'm just not mentioning them because that's a side discussion. We can discuss that in more detail.
That's a detail for knowing what the symmetry is. Or reducing that level.
It does, because you have to understand the boundary brackets, because the soft operator is precisely a boundary mode, and you have to check whether the appropriate, the boundary modes transform in the right way. So they're very important to actually clean up the entire discussion. But those are technicalities and not necessary for just a presentation of the general ideas. But we can discuss them in more detail. So if I just do this for gauge transformations, this entire process, it takes a very nice form, q epsilon q on any sigma, as this is probably just known to you. It's just that. And of course, there's also in 4 dimensions, there's also the magnetic soft theorem. Sorry, not soft theorem, at least the magnetic charges, which you can write down.
Prahar, I'll ask a very blunt
Yeah.
question. It's very blunt.
Yeah, no.
I'm trying to relate this second last equation to Goldstone. Goldstein. So if you've got a charge Q,
Yeah.
it has the property that that Poisson bracket with Q generates the transformation.
Yes. Yes.
Okay, so omega with upper indices,
Correct. Yes.
Poisson bracket with Q on any quantity gives you the variation of that quantity.
Yes.
I presume that statement is related to this.
Yes, this is the infinitesimal version of that statement. And for general transformations, so if I give you charge, you can always derive delta. But if I give you a delta, there may not always exist a function whose Poisson bracket generates that delta. You can write it down infinitesimally at every point, and infinitesimal transformation can be written down, and that's what this first line is. And then you have to check whether that can be integrated over the entire phase space.
What confuses me is why we have a delta Q.
More like omega with lower indices.
Omega with lower indices on the right hand side.
Yeah, contracted with the vector field, which has
That's correct.
Yeah.
But
so
if
the
Yeah.
left hand side will be del mu of the Hamilton.
So this, let me just write down, this equation is, I think, if del mu Q is omega mu nu, and on that side is a delta, so sin mu being the infinitesimal vector field that's generating delta at a point. Right. This is that equation.
and this is an equation actually. So in classical mechanics, that would be, for instance, del Ph is what? What word?
Del H by del C.
Yeah, so in classical mechanics, this will be del H, right? H being the Hamiltonian, del Q is minus the time translation vector, which is a what is it? P dot.
Yeah, from my point of view, it's that the Poisson bracket itself has a derivative.
Correct.
And this is producing the derivative of that.
Yeah.
Thank you.
Yeah.
It has a version in this algorithm.
Yeah, you just take the omega to the left hand side and then
Yeah.
you get Poisson.
Yeah. Yeah. Right. Yeah. So anyway, so if I give you Q, of course you can always derive psi because I can invert this. But if I give you psi, you cannot always necessarily derive a Q.
Right, because there may not be a function to the
Yeah. Exactly. So
That's unintegrable.
exactly. So that's the statement here, and it turns out in the case of gauge series, it is integrable, and that's the answer. This should not probably surprise you. Lambda equal to 1. This is just the standard Gauss's law. This is the statement of Gauss's law. And another thing that you can see that one non-trivial thing that happens for gauge series is that it's entirely a boundary term. So if I were to consider small gauge transformations, lambdas which vanish on the boundary, then the charges are 0. So they're trivial on the phase space. But if I can, there's another thing I can do. I don't just need to choose globals. I can choose arbitrary functions which go to some arbitrary functions on the asymptotic S2, and they give you other non-trivial charges. And so the word identities for those charges is the soft theorem. So let me just write that down. So then let me just forget about, you can always work out with the magnetic guys also. So this guy Q plus lambda basically has the form du times lambda 1 over epsilon squared, some numbers. Okay, and now I use this equation right here to rewrite this charge in terms of those other quantities. So in particular, it takes the form. So let me just write out one of them. So it takes the form del u, let me call dz lambda del u az power plus dz power lambda. So that's the first term. And then I get something else that looks like d to z lambda ju 2, 2, 0, 0. And yes.
And here we were assuming lambda, sorry, we probably said it already. You know, lambda is a function that goes to constant at infinity.
Yeah. No, I mean it's a function at infinity, but it's finite. It goes to something finite.
Yeah, I know that.
Yeah. Okay, so this is the charge that generates these large gauge transformations. And now let's just conjecture that this is a symmetry of the S matrix and just see where we go with that. And I'm not going to go beyond this, but the claim is that this statement, Q lambda commutator with the S matrix equals 0. So this is a statement of this is what it means to be a symmetry, implies the soft theorem. So let me quickly tell you why you shouldn't, at least that the structure of this has the form of a soft theorem. Yes.
So lambda basically is in the number of phase space variables that we have defined.
Yeah.
Lambda has that kind of those many features.
Lambda is a function on the sphere. Lambda is a function on the boundary of a Cauchy slice. So if I was a space-like slice, which is a 3-dimensional slice, the boundary is a 2D sphere. So lambda is just a function on the 2-dimensional sphere.
Why don't you make lambda also a function of u? It would work.
You could, but it wouldn't give you anything interesting because the charges only care about the value of the field on the boundary.
But formally,
Yes.
everything goes.
Formally, everything goes through. It's still a symmetry, but you won't get any new word identities.
Probably
Yeah.
but lambda was that function in your gauge
Yeah.
transformation which took you from one allowed solution to another allowed solution.
Yes, it's the parameter that does the gauge transformation.
So you are allowed to move in the space of allowed data which is given by space with this lambda.
Yes, exactly.
Therefore, as many instances of
Well, no, because it only takes you in a particular way. Like az goes to az plus dz lambda, right? So if I start with a given az, I'm not going to be able to cover all of phase space by just choosing all possible lambdas because I can only move between values of az which are total derivative. So it's a standard gauge transformation. Not all configurations can be mapped starting from a particular point. But this gives you a soft theorem. Let me at least as fast as I can tell you that you shouldn't be surprised that it's a soft theorem because let's look at the structure of the charge. It contains one term that's linear in the fields, and it contains another term that's nonlinear in the fields. So when I take this guy and sandwich it between in and out states, so some arbitrary out state, q lambda as some arbitrary in state. Of course, this has to, I shouldn't write here. Of course, this has to vanish. So this nonlinear piece, which is quadratic in the fields, it basically acting on your out state and transforming it in some non-trivial way. So that's what the right-hand side of the soft theorem looks like. Basically, you take the state and you multiply it by S naught. In the case of the leading thing, it's just a multiplicative factor. More generally, it could be some, as you see, S1 is some derivative guy. And then there's a piece which is linear, which is going to add a new particle to the state. But what type of particle is adding? Are we adding? So let's look at just the u integral over here. So the u integral is du del u az with other terms. So what is this? So let me rewrite this as e to the I omega u, and then limit omega goes to 0. So now you can sort of clearly see what this means. Firstly, I'm doing a Fourier transform in u, which is the time. So the Fourier transform variable is precisely the energy. So this guy is creating a particle with creating a photon with positive velocity with energy omega. There's a u derivative, so I'm pulling down another factor of omega, and then I'm taking omega to 0. So it's picking out precisely the pole. It's multiplying your amplitude with omega, and then take omega to 0. Omega times 1 over omega, only the pole is left, everything else vanishes. So this linear piece is precisely picking out the correct form of the left hand side, and I'm going to ask you to trust me that when I do all the calculations, this picks out the correct form of the right hand side. Okay, this was quite a bit of a review, but now because of all of this, I won't have to say much more when I now do the subleading case.
Sorry to show you.
Yes.
Constantly, but okay. When you say this is the symmetry of the S matrix, you must mean so on one side of the equation, this Q acts on the scribe plus.
Yeah, yeah. So what I mean is Q scribe plus lambda S minus S Q scribe minus lambda equal to 0.
And how it acts on scribe minus is sort of clear because everything is actually just right at the end of that.
Yeah, yeah, yeah.
So, yeah.
The crucial thing, I think, that people, this is basically, I think, why Ashtekar had issues doing, because he was already here, he could have done all of this. But Christodoulou-Kleinemann's work were kind of, the important thing was to identify the lambda sitting here and the lambda sitting there. Maybe in flat space-time it's not that crazy to you and can be easily done, but when I'm in gravity and I'm working in some coordinates, you don't even know if that coordinate can be extended out to scribe plus, and that you have to figure out some non-trivial way of matching the functions that's acting on scribe plus to functions that are generating the symmetry on scribe minus.
So now if I had a lambda that depended on u,
Yeah.
I wouldn't even know what it meant to be, what that meant on the other side. Right?
Yes, because you wouldn't need, well, you wouldn't need it, but what you all you need is that the lambda on scribe plus, when pushed down to scribe plus minus, should map to lambda on scribe minus when pushed up to scribe minus plus.
Yeah.
As long as this is the case,
That's all you need.
that's all I need.
And that's all you can say.
That's exactly. So that is the crucial point, that there is a way to canonically identify the lambdas on scribe plus and scribe minus.
So, what exactly is that way? I mean,
Yeah.
It's this is the mapping that I'm doing, basically. So let me draw a diagram. Okay, and they should be equivalent essentially at spatial infinity. So I did this for flat space-time, but of course all of this works for gravity, where strictly speaking, if I was all powerful, there's really only one. So right now what I've written is there's some symmetry on scribe plus, which is generated by a function lambda. Now a priori there's some other sort of action on scribe minus, which is generated by some lambda minus, lambda plus there and lambda minus there. A priori there are two different functions. But of course, the symmetry of the theory of the S matrix is not, it's not that there's an independent lambda minus and an independent lambda plus. I have to match them in some way, and that diagonal, whatever the diagonal subgroup is, which matches it, that is the symmetry of the full S matrix.
Yeah.
So the question is which diagonal matching do I need to do? Now in flat space-time, you might just say, maybe I'm all powerful, I can just go through the bulk and go out there. But you can't say that in gravity. It's very difficult to do that in gravity. And the work of Christodoulou-Kleinemann is to show how to forget about the bulk and just do everything to just match it in this region right here, where scribe plus and scribe minus meet. Not quite, but the near spatial infinity. And that matching is this thing. So scribe plus at this point, lambda plus at this point, needs to be matched to lambda minus at this point antipodally. And the antipodal matching can be understood from the Einstein cylinder. Like if I were to compactify this on the Einstein cylinder, so essentially lambda that's coming from scribe plus here basically is continuous along the null ray over there. So it's matched to the antipodal point on scribe minus.
Even when you have some new dependence on lambda, so you can say the same statement. Why is it a problem if you have new dependence?
It's not a problem at all.
Okay.
It just won't get anything new.
That's fine, that's fine. You know why I'm asking.
Yeah.
Okay, so you can do that. This
How can you do it? You've got u dependence, which is u
Yeah.
very here, and then v dependence there. And how do you connect the u?
No, you just match it there. And the point is that you can
Since
choose.
it doesn't matter.
Yeah,
you
yeah.
match it. But
Yes.
had it mattered, you would
Oh,
know what to do.
absolutely. Yes, exactly.
if you have a new
Very
dependence on scribe plus and new dependence on scribe minus,
Yes.
then you are saying there is no way you can make some statement like
Okay.
How would you
So in other words, if I ask you what is lambda plus at u equal to 0, how is it related to lambda minus at v equal to 0? You can't say that.
But there is sort of, the main point here is that you have a common point. Sort of
But only that's the only common point. So that's the point where you can hope to match. Everywhere else, you can't say anything.
the thing is here,
Yeah.
the point is that you have a point which is common to this guy and that guy, and you want your quantities to be continuous. And
Yes.
you go along the null generator in this diagram, in this compact square diagram.
Yes.
As you go past this point, this point,
Yes.
you want things to be continuous.
Yes.
That determines the antipodal mapping.
Yes.
And if you have a U dependence, then there is no, you cannot make an analysis.
No. So if I do have a U dependence,
Yes.
the matching that I'm looking for
Mhm.
is the entire lambda minus needs to be given in terms of lambda plus for all values of u and all values of v.
If my charge will contain only information about lambda plus, psi plus, let's say.
No, but that's because in this case it doesn't matter. Like if there was a charge which cared about the exact profile of lambda plus and lambda minus for all values of u, if the charge was of that form, then in order to have a diagonal subgroup, you need to tell me what is lambda minus entirely as a function of lambda plus, for the entire function. And that just cannot be done because there is no map.
So let's work with this nice charges. We just cared about the boundaries.
Yeah, in that case you can do whatever you want. Put arbitrary u dependence, nothing will change.
Nothing will solve it.
Yeah.
That's all.
Yeah. Okay.
Yeah, this
Any more questions?
Okay.
Okay, so now let me go to the subleading soft theorem. So now we all understand, I hope, this covariant quantization picture.
I'll ask one last question.
Yes.
Okay.
Yeah.
You said the phase space was this A0
Yeah,
as a function of three variables.
yeah.
And is that completely precise? Is that some finite data? Is that 100% precise specification?
No, well, there are some other dynamical constraints that one, because at every order in R, the equation is du of something is a source that's known by
Yeah.
previous orders in R.
Yeah.
So at every order in R, you will get some u independent integration constants.
Okay.
And you have to fix those. So those are in principle also the data, but that is precisely this data. That is precisely like this data right here, this data right there.
So if you throw that away, is it precise?
Yes, then it is precise. Yes, okay.
Once I just put the diagram of those conversion and
Yeah, those and many more actually. That's the discussion. The part I didn't understand was why the Penrose-Newman constants. The Penrose-Newman constants were just particular L modes at every order in N. At every order in R, you pick out a particular L mode, and that's the Penrose-Newman constant. But in principle, at every order in R, you have a whole function's worth of constants also on this S2. But for some reason, I think a particular L mode is more important. That's the part I don't fully understand. Okay, so we have understood at least how this leading guy works, and we've also understood the problem, at least naively, of generalizing this to the subleading case, because how could the subleading case depend on higher derivative terms? Okay, so in order to do that, let me go back and write down this formula here for the gauge theory without taking the large R limit. Just I'll leave the large R limit explicit. I'll keep the limit R goes to infinity explicit, and then let's just see what we get. So if I do that, you get the equation that looks like delta Q epsilon of a certain guy. So now I'm doing this for the action that I wrote down, phi f squared interaction term. So this just looks like 1 over u squared delta f u z Okay. So this is just what I get. And the point is that if I choose my deltas to be tangent to the phase space, then delta A has to have the same fall off as A itself. Otherwise, you're not moving tangent to the phase space. So if I assume that, which is what I was doing in all of everything here, this term drops out. Because phi falls off like 1 over r, f is order 1, and A is order 1. So delta A is also order 1. So this entire term, dimension 5 term, falls off like 1 over r. So it just doesn't contribute in the large R limit. This is the only order 1 term that contributes.
That additional term came because the symplectic form is modified?
Yeah, I mean, as you see, if I take R to infinity, then it's not modified. But of course, everywhere in the bulk, the symplectic form cares about the full
The
action.
momentum conjugate has contribution from the
Exactly. Yes. Yes. Yeah, but this is still a true fact simply because when I take R to infinity, all of these extra terms drop off in this way that I've described. So this was the reason. This is going back. This is the point. This is the point where if I were to take R to infinity, assuming that this capital delta has the same sort of fall offs as the fields themselves, I'm not going to get anywhere. So clearly, one way to fix this is to sort of include the contribution of this term, is to choose a delta which is order R. Then this cancels this 1 over r fall off here, and I get something finite. Now immediately you might worry that this becomes divergent, because that's order 1 and that's order r. So I get a divergence from that. That's certainly not good. But I'm going to ignore that for the moment and keep writing it, and then see what we get. I'm going to take the limit r goes to infinity at the very end. So keep all divergent terms and see if we can cancel out the divergent terms in some physically meaningful way. Okay, so now we know that we want to choose a delta that grows like order r, but what delta should that be? The simplest example, now we know we're dealing with gauge transformation, so let's just do a gauge transformation which grows like order r, which is linear in r, and see the charge and see what charge we get. So remember, I was working in all these formulas I've written over here have been derived in Lorentz gauge, though the results are gauge invariant. So the lambda that I'm allowed to choose, because I need to preserve Lorentz gauge, has to satisfy box lambda equal to 0. And in addition, as I've just said, I'm interested in looking for lambdas which are order r. So you can then solve this equation, and you will find that lambda has to be of the form r times mu. This mu is a function only of z and z bar, has no u dependence, plus u over 2 d square plus 2 mu plus order 1 over r. So clearly, these are the sort of gauge transformations I now need to do, that I now need to consider and construct the charges for these things, so that this guy can potentially contribute. Okay. Okay, so I'm just going to write out what the answer is. So the answer turns out to be q scri plus is a function of this mu, as expected has a r divergence coming exactly from this term. So you have an r divergence. Let me write that down, and then there's a finite piece. Oh, capital D is the covariant derivative on the sphere. D square is Laplacian on the sphere.
How come the order R piece and the order 1 piece are not independent?
No, there is an of course, if I fully solve it, there's an epsilon there plus order 1 over r. There's an independent data over here also. But this epsilon is just the charges that I wrote down previously, the finite gauge transformations which give you the leading soft theorem. So we've already discussed this piece. Now I'm interested in the piece which is this divergent piece.
So this epsilon is just epsilon of z bar.
This also is just epsilon of z bar as it was previously, and it generates the standard gauge transformations. Okay, so it's of this form. There's a divergent piece. There's a finite piece. Let me write down what the divergent piece is. No, sorry, let me write down what the finite piece is and I'll tell you about the divergent piece. Plus complex conjugate. And this, I've sort of, maybe I shouldn't have, but I sort of, to show the universality, this is always the structure for any theory with any higher derivative term. And for the theory that I'm currently writing down, Jz bar is just phi f uz bar times 2g. But the structure is always just that. Okay. And the nice thing about this order R divergent piece is that it's precisely equal to the leading charge that we had written down just previously.
Physically.
Yes. So the charge is divergent. Now if I take a large R limit, I'm going to get something divergent. But let's consider the Ward identity. If I now consider the Ward identity, the divergent piece vanishes because of the other Ward identity, the leading Ward identity. So the Ward identity, now after you write down the Ward, then you can take a large R limit and you get something that's completely meaningful. So even though the charge is divergent, the Ward identity is completely finite. And you can extract information from there.
So another way of saying it is you don't ever need to look at gauge transformations before it comes. You take what you get from here and
Yes.
solve the number for 1 by r.
Yes, exactly, exactly.
The epsilon is some small correction too.
Yes, so if I just get this, then I just get Q leading sky plus epsilon.
And that just shifts with r.
Correct, correct. Right? So the Ward identity is still finite, and now, so I can write that down, and it's basically just the Ward identity I would get from this term. So let me just, now we have the charge, and basically we do the same analysis as before. And let me sort of use that to explain everything else that we need to, that we needed to show. So firstly, let me convince you that it is generating the subleading soft theorem. And to do that, we'll do again what we did previously. Let's just look at the u part of this entire thing. So integral du u del u az. And I think this can be written as limit omega goes to 0 of 1 plus omega del omega integral du so you can do you want me to check this? So you can check this. So when I add 1 plus omega del omega on this e to the I omega, I get 1 plus I omega u. And then the omega piece I can rewrite as I omega piece I can rewrite as del u. So 1 plus u del u acting on this guy is simply del u total derivative of u times e to the I omega u. And then I can integrate by parts. So I get that. And then take omega to 0. Okay? So, now, so this is just exactly equal to that. But now we do the same analysis. So again, it's linear, so it adds a particular photon. It's adding a photon with helicities plus. Do a Fourier transform, so this quantity creates a photon of energy omega. The 1 plus omega del omega is a projection operator that kills off the 1 over omega term. And then I take an omega goes to 0. So all the other higher order terms cancel. So this guy precisely picks out exactly the subleading term, subleading soft part, so S1. And then you could, I'll convince you that I won't convince you, but I hope you will be convinced that the rest of it will work out exactly. Otherwise, I wouldn't be giving this talk. But let me, in the least, tell you why the universal structures and all can be explained. Firstly, you note is Jz bar, which sort of tells you that Jz bar being a negative helicity guy, if it acts on a particle, it reduces the helicity by 1. So this immediately sort of explains the action of f hat. The universality of the kinematical structure, you will notice from the following fact that the entire kinematics is sitting inside of this dz of mu, and there's an entire structure here. So in order to localize this to a delta function, like that's how I need to get a photon at a particular angle. I need to localize this entire dz bar of d squared mu to a delta function. So I need to choose a particular mu for that to work. And for that same choice of mu, I'm going to get a very particular type of function here, not something completely random. And that exact function is the thing that's appearing. That's why it's universal. It's sort of independent of this jz bar. It doesn't care what this jz bar is doing. Everything is just coming from this mu, and you have to choose a particular mu to get the soft theorem. So even that is then explained. Good.
You'll have to explain why the leading term is also R.
So he said that leading term was proportional to the leading soft theorem.
So this divergent piece, the coefficient of that happens to be.
Oh, you didn't have to show that in the. Okay, got it.
Yeah.
You didn't have to show that in the chart.
Yeah, I'm not claiming the charge is finite,
Yeah.
but the ward identity is finite.
Got it. Yeah. Thanks.
Okay, and this works, gives you precisely the thing with all the higher derivative terms in exactly the way that. Okay, so I've already answered. It's now clear that because of this argument, if I give you a dimension 6 term, that will fall off like 1 over r squared. So in order to keep that, I would have to allow for order r squared divergent gauge transformations in order to keep that. So why shouldn't I do that? So now that I'm allowed to do all of these r terms, why can't I do order r squared terms also? And the answer is basically this, is that you'll never be able to write down a finite ward identity, because if I allow for an order r squared divergent gauge transformation, the charge takes the form q is r squared q leading plus r times some q divergent here plus q finite. But this q divergence is not equal to the subleading q at all. It's not related to that. It's some totally different object. And there's no reason that this guy has a vanishing ward identity with the S matrix. So if I were to take the ward identity of this guy, I would be able to cancel out this, but I would still get a divergent piece coming from this guy.
So that sounds like you're arguing after knowing the answer. I mean, how did I know that there weren't 3 soft theorems? So that this, that, and that were all 0. Suppose the answer had been that there were 3 soft theorems.
You would have now 4 soft theorems.
Actually, why 4?
Because you already have 2. Now you have another one here and another one
Suppose
there.
the rule for some reason I didn't know is that you're not allowed to take R gauge transformations that behave like R, but you are allowed to take gauge transformations that behave like R squared.
Yeah.
For whatever reason.
Okay.
Okay, and then you're supposed to Taylor expand whatever you get there. Then you would get these 3 bits here.
Yeah.
I mean, it's a little bit like you're telling us the
I'm explaining the answer. I'm
You're
not.
explaining it.
The
rule is not completely systematic to you. Let me ask another question.
Yeah.
Well, maybe after you.
Well, this is kind of all I had to say. I just wanted to argue that, this sort of explains why you don't have subleading soft photon theorems, and this is the limit, because you don't get anything sensible from this. But I understand Shiraz's question. Why don't we just impose it and see what we get?
Okay.
Yeah.
In fact, you can ask more. You can say that all the things that you did with charges, all of them are gradient until the moment when you decided that, then why to draw it? You can ask this kind of question. This form.
Lorentz gauge was just a convenience. In a different gauge, my lambda would have a very different form, but of course the charges would have the same form.
So, I'm just saying that if I choose a different gauge, can you always write down a suitable lambda function? I know if, all of my question is that when you related these 2 coefficients,
Yeah. I used box lambda equal to 0.
you use
But the thing is, in any other gauge, you would have to use.
I mean, if I work with, let's say, let me just work with something, I know, all I am saying is that, can you work in it's not, my point is not anything else. I know that, I understand it's giving a very good explanation, but anyway, so it's a question. If you work in AU equal to 0, then how would
Yeah, then the set of symmetries, you would have to define it in some different way. You have to put in some other prescription that explains. why the order r and order 1 terms are related.
Some gauge, if there is some gauge invariant principle which says how these things are related,
Yeah,
once you learn
yeah.
them, it will be nice.
Yes, I completely agree.
In terms of this, like, go up in the chart.
Yeah.
Are you saying that having done the diagram of the property,
I mean, there is some sense because you can now ask, okay, so it seems that the only word identity is this Q finite. So you should maybe think of that as the physical thing that's acting on the Hilbert space and give. The action of Q finite has nothing to do with gauge transformation. It's doing something totally weird. Like you can already see by this structure right here. It's doing something so totally weird. It's taking, I mean, as we know, as it has to from the soft theorem, it's taking a photon and mapping it to a scalar field. Right? That's not what a gauge transformation does at all. So if this has always bothered me that what is, because this is sort of a symmetry that's acting normal to the phase space. There is no proper interpretation of this as some action tangent to the phase space. And if you try to give that sort of interpretation, it's divergent, it's pushing it onto the phase space. So for instance, it's not conserving any of the fall-offs for the gauge fields or the scalar field or any of those things.
but there has to be anything that cannot be an analysis where to give you a systematic routine.
No, I think there is one.
That is one.
I think there should be one, where you don't have to deal with these divergent gauge transformation. This is something that I've actually totally not understood. I'll give you another example where both sides are known, but I'm not at all clear. So subleading of graviton theorem. Now we know that that comes from superrotation. That's sort of a well-defined within the phase space language of describing it, and it comes from superrotations. But you can also consider divergent supertranslations. And you go through the same process and it gives you the same word identity.
In the sense that also the charges are divergent.
Charges are divergent, you pick out the finite piece, and the finite piece again has nothing to do with supertranslations, but it has some other meaning altogether, and you can write down some word identity and gives you the correct. So what is surprising to me is that the divergent part of the divergent supertranslation charge is the superrotation charge. I don't see why that should be true at all, but it seems it is true, and it seems like that, at least in that example, there is an alternative, completely well-defined definition of how to write down the charge. That has not appeared here.
So in that example,
Yeah.
is this equal to again an analysis, how to relate these two gauge parameters, this kind of analysis?
In that example,
So you have a is it that your divergence is an overall divergence, or it's a
it's of this form.
so it's a relative divergence. I use a relative because one of them is diverging, one of them is not.
Yeah.
So in this sense, you need to relate these gauge parameters in the divergent one and the non-divergent one.
Yeah.
The one that you get.
Yeah. In the gravity case, they just do it in Bondi gauge. You can then relate the subleading terms in the.
Comes out of the gauge. This relation here that is derived.
Yeah, it comes out of some
That
gauge.
A and is assumption.
Yeah. Yeah.
Sorry, could I ask you, suppose you take electromagnetism on a spatial cylinder and you put some appropriate boundary condition on the cylinder.
Yeah.
I will eventually take the cylinder to be as large as you.
Yeah.
Now, then, I suppose it's consistent to put some sort of Neumann, some sort of a condition where you leave A on the boundary free, but its normal derivative goes to 0.
Yeah.
If so, you would allow gauge transformations that are non-vanishing on the boundary.
Yeah. Yeah.
I was wondering whether, if one worked out this problem, whose rules would be very clearly defined because there's no infinity,
Right.
and then take a suitable limit, whether you could recover from it.
I think, I mean, we are partially doing that, right, at some point, but I think, yeah, that has to be done carefully. Maybe that is,
Maybe that will tell you why some things are allowed and some things
Yeah.
are not.
yeah. I mean, in principle, there's a, yeah, I completely agree with all the comments. There should be a, like, proper phase space sort of analysis which fixes exactly the sort of epsilons that I should be allowing.
So what might be happening
Yeah.
I mean, it's the opposite of doing small gauge transformations. You have gauge transformations which give you some finite charge. You do some small gauge transformation on it, doesn't change it. So if you do a large gauge transformation, it can add a divergent field.
Yeah.
That will grow to a charge, but
Yeah.
but probably the divergence is such that it doesn't matter. Maybe.
Yeah. No, but
Guessing.
I keep feeling like there should be some description of the symmetry which gives you just Q finite, with nothing else keeping you in the phase space and all of those nice things. That yeah, that as I said. So what Strominger and Sabrina and Lysov did previously was to start with the subleading theorem and go backwards. And of course, when you do that, you will never get divergence. You just read off finite. So that's what they got, but they could not make any physical sense of that symmetry. It was not clear at all why that should be a symmetry, where that's coming from, or anything of that sort. What was interesting that you could reproduce that from this large, but the same thing is true also in gravity. What is very interesting to me is how is it that divergent super translations knows about super rotations? They seem like totally different things qualitatively. So why should there be any relation? Yeah.
Could there be anything said about expansion even in this 4 dimensions? What could it be that because we are looking at, if you look at a field in a wrong place, it look divergent. What I mean is, suppose you have a function which is very nice.
Yeah.
Now you start expanding it at wrong places. You will see that the things are divergent. Just because you do not have the whole form of the function.
Yes.
Could it be that this is basically there is some nice Q master Q kind of thing which has very nice behavior? Now we expand it and you see all sorts of problems because you have to go expanding around and things are simulated and something. I know my comment is vague. I'm just saying that.
Well, gauge transformations, you could choose any function a priori, right?
Yes, but the fields are nice. The fields are great. They are supposed to be good quantities. Now, this is like a function worth of charges.
Yeah. Well, I don't know. Scribe plus seems like a naturally nice place to deal with massless particles. I would not think that if I have all nice functions there. Let me give you one more thing. Let me say. Actually, I think. Yeah, I just remembered there's, I think, a better way to explain this, which does not deal with these phase space things, but sort of, Andy has another way of looking at these symmetries, is start with the matching conditions. Forget about all of these phase space and to simply say that there exists a quantity which you can match across scribe plus minus in this way. And so in this way, as I said, so suppose there exists some quantity, some field, some field that I have, which happens to have this special property that when I give you a profile on scribe minus, I evolve it into the bulk, do all sorts of complicated things, and it comes out in the future. The properties of the equations are such that the field evaluated at scribe plus minus happens to be equal to scribe minus plus. Suppose this is the case. So suppose there exists a field phi whose value at scribe plus minus is equal to the same field phi at scribe minus plus, antipodally. Now what I can do is I can always create a function which has that same antipodal matching condition. And actually, no, I don't even need that. So this is some function on the celestial sphere that happens to have this matching, right? Now take epsilon to be any function on the sphere, multiply both sides by epsilon, and integrate.
The function from the past is scalar function from the future. That's
Yeah. Yeah. So this is a conservation law, right? As long as you can find a field that satisfies this matching condition, there is an infinitely many charges. There exists infinitely many charges, and therefore infinitely many Ward identities,
So
which
this
you can then
requires
construct.
an analysis of the property.
Yes. So if viewed from that perspective, actually, there's a much better understanding of these problems. The large gauge transformation the leading soft theorem is coming from the matching of FUR2. And the subleading guy is coming from the matching of FUR3. And you can't match anything below that. FUR4 doesn't get matched. Well, I don't have any analytic way of proving it, but I'm working backwards. I'm presuming that there is some proof which you can use to show that FUR4 does not get matched. Therefore, there is no subleading soft theorem.
So you just take an arbitrary source in the bulk and look at the property
Yes.
and just check.
Yeah, actually, this is easy. Linear theory, gauge. This is a linear theory. You can probably just prove it. Yes.
So if you have 4 and all get determined in terms of proof.
No, so as I said, at each order there are some. Yeah, they're all determined in terms of your data. So, but they happen to be matched, right? That's
On the same
on near spatial infinity, just there. So as maybe that's just a better way of looking at it. You forget about all of these. Just like if there exists a field that you can match, then you can write down infinitely many then you can write down word identities for every such field.
That's very near to the scattering amplitude way. I mean, you're saying that when you compute Feynman diagrams, you will always find these things matching.
Yeah.
But the phase space thing brings in a new angle, right?
I agree.
What if you have a line of flu where of points, just all the points of the have charges, infinite line of that, then
I remember.
so you have let's say you think a straight line. You have a straight line in space. At every point you have a charge density.
Straight line in space for all that. But no. Okay.
Now your electric physics things will have now log or some size. I'm saying that the statement that you said that study with an arbitrary source, it depends on the source that what kind of behavior you get at infinity.
I mean, of course, there's some physical constraints you have to impose on the source.
Yeah.
There's no doubt about that.
Yeah, you're not going to allow it to go to space. It's not a spatial thing. You can allow it. Like a particle.
There's somewhere sitting in the origin. Infinite.
So, I mean, yeah, you can violate this. The kind of thing that we do in scattering, the kind of thing that will arise from Feynman diagrams, you can just check.
Yeah.
How this
So you are saying, so the kind of thing we do in Feynman diagram, you do those.
Yeah, you do
Yeah,
those
I mean,
and just check.
yeah.
By the way, so this I think I had already been asked by the guy, but in the context of the subleading graph.
Yeah.
So suppose I just construct the following chart. This is R squared Q leading plus R Q subleading plus Q finite.
Yes.
This is a formal construct.
Yeah.
This is not what will get some, your method, but it will generate something. It will generate some kind of class of divergent large space class.
Yes, it would. But these charges would not commute with the S matrix, right? The point of all of this is we are conjecturing that a Q commutes with the S matrix and then checking whether that's true. If you want to look at it the other way, we just impose it to be true and derive the soft theorem. Then you can maybe impose this to be true, that this commutes with the S matrix separately, and you derive some property which is not going to be satisfied.
But Q subleading was already
In that case, now suppose I was considering order R squared gauge transformation, then this coefficient is precisely the leading charge. So this we already know has a vanishing word identity. So this guy goes away. That's very nice. But this divergent piece has no interpretation in terms of any of the previous charges that we've written down. It does not generate the leading charge. It doesn't leading soft theorem. It doesn't also generate the subleading soft theorem. So a priori, there is no reason to believe that this guy commutes with the S matrix.
Why should it commute with the
I mean, if you want a finite word identity.
No, what I am saying is
Okay.
I just couldn't
Yeah.
If I have rotations in my matrix assembly,
Yeah.
so you are saying that I asked this question.
Yeah.
And then could it be that this guy does not annihilate the S matrix but transforms the S matrix in like this?
No, but then that's still not good. I want to kill off this divergent, right? I want to have a finite word identity.